Hello again. What if we were faced with the example that we wanted to find all real zeros of that same polynomial we talked about in the last video? F of x equals x to the fifth minus 5x to the fourth plus 12x cubed minus 24x squared plus 32x minus 16, and then factor it. I don't know about you, but when I look at this, I don't know factor, strategies pop out at me. All right, well, we're going to do this by using another theorem, which is starting with another theorem that's called the rational zeros theorem. It says that if f is a polynomial of degree bigger than or greater than 1 of the form, remember our friend, a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus ... plus a1x plus a sub 0, where a sub n is not 0, the first coefficient, and a sub 0 is not 0, with all integer coefficients. So we're saying that all these a sub n's, a sub n minus 1, a sub 1, a sub 0, are all integers. The theorem then tells us that all rational zeros, remember what a rational number is, numbers that can be written as fractions, are of the form p over q, where p is a factor of a sub 0 and q is a factor of a sub n. So we get factors of a sub 0 on the top here, of the constant term, and factors of the leading coefficient on the bottom. All right, let's put it into action. So if I'm looking for zeros of this function, I know I can test them using synthetic division, the remainder theorem, and the factor theorem. But where do I start? Well, that's what the rational zeros theorem does for us, is it narrows down which things could possibly be the zeros, okay? So all rational zeros of f of x are of the form factors of the constant term, which is negative 16, over factors of the leading coefficient, which are 1, right? So what are the factors of 16? Pardon me, negative 16. Well, plus or minus 1, plus or minus 2, plus or minus 4. Oh, goodness. Sorry about that. plus or minus 8, and plus or minus 16. What are the factors of 1? Well, plus or minus 1. Okay, so if all my rational zeros are of this form, then I know that the possible rational zeros, or the rational zeros that I need to kind of test to see if they are zeros, are plus or minus 1, which I get by taking plus or minus 1 over plus or minus 1, plus or minus 2, which I get by taking plus or minus 2 over plus or minus 1, plus or minus 4, same way, plus or minus 4 over plus or minus 1, plus or minus 8, or plus or minus 16. Now you might say that's a lot of possibilities. We have 2, 4, 6, 8, 10 possibilities. But that's a lot less than infinite numbers of zeros that might be possible. And you'll find out that we don't actually have to try them all to find some and to make our job a little bit easier of factoring this. Okay, I'm going to start at the beginning. It's often a good idea to start at the beginning. I'm going to start with the number 1. Okay, is 1 a factor, right? Or I'm sorry, is 1 a 0? Is 1 a 0? Another way to say that is x minus 1 a factor, right? Well, according to the remainder theorem, or the factor theorem, if x minus 1 is a factor, then f of 1 would be 0, and we can find whether or not f of 1 is 0 by using the remainder theorem. And so what I'm going to do is take synthetic division by a 1 and see if I get 0 as its remainder. Okay, now let's go back to what our coefficients are. I can't get them on the screen. They are 1, negative 5, 12, negative 24, 32, and 16. Okay? I'm going to bring down the first number, 1. Then what do? 1 times 1 is 1. Adding negative 5 and 1 gives us a negative 4. Negative 4 times 1 is negative 4. 12 minus 4 is 8. 8 times 1 is 8. Negative 24 plus 8 is a negative 16. Negative 16 times 1 is negative 16. 32 plus a negative 16 is a positive 16. And then 16 times 1 is 16, and I just realized that this last coefficient up here was supposed to be a negative 16. So that when I do add negative 16 and 16, I get 0. So again, by the remainder theorem, I know that f of 1 is 0, right? That's the remainder I got. Thus, by the factor theorem, x minus 1 is a factor. Yay! Okay, so watch what I can do. You know that if you factor polynomials, you're going to write them as multiplication. So I know one of the things that I'm going to multiply together to get f of x. Watch what the other one is. When we do this process of synthetic division, it gives us more than just the information that 1 is a 0 or that x minus 1 is a factor. We also get the new coefficients of the other factors. So this 1 here, right, this 1 here, is going to be a new coefficient of the next factor, which is going to be 1 degree less than what we started with. So I'm going to get 1x to the 4th, or x to the 4th, minus 4x cubed plus 8x squared minus 16x plus 16. So notice that I have the coefficients that I circled in red are all the coefficients of these terms. 1, negative 4, 8, negative 6, 16. And the degree goes down by 1 because if we were to, distribute this x minus 1 times this other factor, the first term we would get would be x times x minus 4, which is x to the 5th. All right. Yay! So we found one linear factor of f. That gives us a 0. Let's see if we can find some more. What we're going to do now is we're going to say, okay, let's try 2. Yeah. So let's look at 2, and we're going to now only list the coefficients of this new factor here, right? Okay, because if we divide by x minus 2 and we get 0, we know that it's a factor of this other polynomial that I just underlined in green, which means it's also a factor of f of x. So I'm only going to list the coefficients of x to the 4th minus 4x cubed plus 8x squared minus 16 plus 16 because it gives me a lot less work to do. I'm going to bring down the 1. 1 times 2 is 2. Negative 4 plus 2 is a negative 2. Negative 2 times 2 is a negative 4. 8 minus 4 is 4. 4 times 2 is 8. Negative 16 plus 8 is a negative 8. Negative 8 times 2 is negative 16. Woohoo! I got a 0 again. So this tells me that f of 2 equals 0, which then means that x minus 2 is a factor of f of x. Alright, so what do we have so far? Earlier we found that x minus 1 was a factor. Now we know that x minus 2 is a factor. And our leftover polynomial is again what I've underlined here in green. These are the coefficients, I should say. And we're going to go down by 1 degree again. So now we're down at x cubed. So 1x cubed minus 2x squared plus 4x minus 8. Great. Now that we're down to a cubic with 4 terms, this might be something we could factor using techniques of factoring. So that's what I'm going to do here. I know that I have x minus 1 and x minus 2 as factors, and this would be a nice review. I can group x minus 3 and minus 2x squared together. I can group 4x minus 8. Remember, this is called factor by grouping. When I factor by grouping, I take out the LCD of each group. So we get x squared times x minus 2 plus 4 times x minus 2. And then I notice that I have a common binomial factor inside these brackets of x minus 2, and then x squared plus 4. And actually I don't need those brackets anymore, so I'm just going to go ahead and get rid of them because that's really easy for me to do. Okay? Now it's looking to me like this is fully factored, right? How do I know that? Well, this x squared plus 4, right? Is it factorable? No, it's the sum of squares, so I can't do anything. All right? So now that I'm finished with this, I can say what my zeros are, right? My zeros are 1. That comes from the factor x minus 1 with multiplicity 1. I have another 0, 2, but notice it happens in 2 factors. So my 0 is 2 with multiplicity 2. And those are my only real factors, since x squared plus 4 equals 0 has no real solution, right? So these are indeed the real zeros of f of x. Okay? Let's think about this function a little bit more and see if we can graph it. We know it's zeros, right? Do we know its y-intercept? Its y-intercept, of course, is f of 0, which if we go back to the original function, we plug a 0 in for every x, they all disappear except for that constant term. Okay? So I've got my x-intercepts or my zeros, my y-intercept. We know that it's a 5th degree function with a positive leading coefficient. So as far as end behavior, it's going to kind of look like this, and then some things are going to happen in between we're not sure of. Okay? So we would have enough information to go ahead and graph this, at least very cursorily. So we have 1, 0, 2, 0 as our real zeros, and we also have 0, negative 16 as our y-intercept, right? 2, 0 is at 0 of multiplicity 2, which means our function's going to touch the x-axis there but not cross it. 1, 0 has a multiplicity of 1, so it's going to cross, and of course we're going to cross right through the y-intercept. So this is kind of a rough graph of what this function looks like.